I had thought that I would do the full derivation of the curl of B and the divergence of B for you, but on further consideration I decided that it was fairly uninstructive. I would show you, or I'd indicate to you how we would go about such a calculation, and if you're interested in the details you can look it up in any one of the classic books. So the procedure is of course very similar to the procedure we use to study the divergence of the electric field and the curl of the electric field. So we write down our equation for the magnetic field. And we simply take its divergence. And what you'll remember from our study of electric fields is that when we take the divergence, we're taking all the derivatives with respect to the unprimed coordinate. So the derivatives then, of course, are going to come straight up inside this integral, because the integral is over the r-primed coordinate. You can pull the derivative inside that integral, and you can do some fairly uninstructive manipulations, and what you will find is that the divergence of the magnetic field is equal to 0. And this becomes one of our Maxwell equations. It is true whether we are dealing with magnetostatics or if we include time-dependent magnetic fields. By a very similar procedure, we could take the curl of the magnetic field, and once again, all the derivatives come inside the integral that I've written above, and we would find that if we took the curl of the magnetic field, that this would be equal to mu naught times the current density. And you'll notice here, again, as with electrostatics, that this is all local, in the sense that the curl of the magnetic field at position r is given by, or mu naught, multiplied by the current density at the same position r. And I should be clear here once again that this, of course, is a vector. So the two equations I have here are important and useful equations in magnetostatics. The second equation is valid only for magnetostatics. It is not true if we have time-varying magnetic or electric fields. The top equation, however, that the divergence of B is 0, is always true. Okay, so before we close out this initial discussion, or this first lecture on magnetostatics, let's just make a quick comparison of magnetostatics and electrostatics. Okay, so here then is our comparison. You'll notice that the sources enter differently in magnetostatics and electrostatics. You'll see that the source term in magnetostatics enters into the curl equation for B, and the source term in electrostatics enters into the divergence equation for E. Okay, other than that, all right, well, we have some similarities, some other similarities and differences. The divergence of B is 0, and it is always 0. As a consequence of the divergence of B being 0, we can always write B as the curl of another vector field, and that vector field A we call the vector potential. In electrostatics, as a consequence of the curl of the electric field being 0, we can always write the electric field as minus the gradient of a scalar potential. So this is the what do we call this? This is the what do we call it? Let's call it the potential, the scalar potential in electrostatics. This completes our initial discussion on magnetostatics, and in the next lecture we're going to have a look at calculating with the equations that we've developed for magnetostatics.